Okay.
Okay, hello everyone. Welcome to Crypto Cafe. I'm very happy to have Kelvin Abu Haidar, who was a PhD student at ENS Lyon with Damien and Alain. His main topic of research are lattice-based constructions of basic cryptographic primitives and recently side-channel attacks on post-quantum schemes. He's now a postdoc at NTT Social Informatics Lab in Tokyo, working with Mehdi Tiboshi. Today, he's going to talk about Rowhammer, a key recovery attack on Falcon. Over to you, Kelvin.
Hey, thanks, Deepayan, and thanks for the invite. So yeah, as he said, today I'm going to present to you a recent paper we had at Crypto last year called Rowhammer, which is like a key recovery attack on Falcon. So let's start with a bit of trivia on Falcon. So what is Falcon? It's like the recent, not so recent now, but like a standard from the NIST called the FNDSA for post-quantum signatures. It's an efficient scheme, but a complex one at the same time. It's complex because it uses floating point arithmetics, which makes implementing it securely on embedded platforms very tricky, and a Gaussian sampler, which makes it really like sensitive to side channel attacks. So in Falcon, we work in a polynomial ring, which is zq to the x quotiented by xn plus 1, and over a modulo q, which is prime. Over this polynomial ring, we construct what we call an NTRU lattice. So we won't really care about the specifics in this talk, but basically the advantage of this NTRU lattice is that we can generate very short. What I mean by short is made by short elements. So like we can generate a basis that is made with small elements. And this basis that you see on the bottom left is going to be the secret basis, which will be a good basis for some definition of good that we'll see later. And you'll have on the right side, the bottom right, a public matrix, which would be a bad matrix. And part of the secret key is the good matrix and a Falcon tree, which we'll also see later. So to understand how to sign in Falcon, we need to come back to something a bit older called the NTRUSign. And especially we're going to come back to what we call the nearest plane algorithm, which allows to define, like to make basically a notion of signature of the lattices, over the NTRU lattices at least. So if you take the nearest plane algorithm, you have like a basis of a lattice. So here you can see it in 2 dimensions. You first compute the Gram-Schmidt orthogonalization of this basis. So this gives you something that is not a basis of the lattice anymore, but is a basis of the ambient space. And it's an orthogonal basis here. So it's not orthonormal. It's an orthogonal basis of the ambient space. And the nice property it has is that you see that the area in gray here in the rectangle is going to be the same as the area spanned by the parallelepiped spanned by the original basis. So once you compute this GSO basis, what you can do is you see this rectangle, this gray rectangle, you can center it in the lattice point. And if you do this for every lattice point, you get a paving of the space. So now each lattice point will have its own rectangle. The rectangle don't intersect, so we have a paving. And so, for instance, if you take any point in the space, you're going to have only one rectangle in which it will fit in, sorry, and this rectangle will correspond to a lattice point, right? So this is exactly what we use to solve what we call the closest vector problem. So here the approximate closest vector problem, and this will be a signature in a way we'll see. So if I give you a random point in the space, here the green point, we can use this method I described. So you identify in which rectangle it falls, and the rectangle is associated to a lattice point. So you're going to say that for you, given the basis that you have, the closest vector is going to be this lattice point. So of course it's not going to be like necessarily the closest vector. So that's why it's approximate. And the quality of this approximation will highly depend on the original basis you have. And that is why we have a notion of good basis and a notion of bad basis. Is the good basis are the one who will allow you to have very good approximation of the closest vector. So they will give you very good results, but the bad basis are the one that will give you bad result. And basically a good basis would be like something that is very close to orthogonal already. And why is this a signature? Well, this point that we have, this green point, you can see it as you could hash your message. So you want to sign a message, you hash the message. This gives you a random point in your space. And you could say, okay, if I want to show you that I know a very good basis, which is my secret in Falcon, then I'm going to give you this approximation of the closest vector. And what you can do is check if it's a good approximation, then I must have this good basis, kind of, right? And if I cannot give you a good approximation, then I must not have it. So that's why it's kind of a signature. And this signature style was first implemented in NTRUSign, and it was also broken 20 years ago by Nguyen and Regev. And the reason it's broken is not so clear from the way I presented it, but it becomes a bit clear when you notice that everything I described here is deterministic. And what you could do is, okay, now I give you this approximate closest vector problem, this approximate closest vector, which is the signature. And what you can do is always center back the point into the rectangle corresponding to zero, right, to the lattice origin. And so once I give you a few signatures, what you can see is that basically you get access to a sampler in the gray area, in the rectangle around zero. And so if I give you a lot of signatures, then I basically leak the geometry of this rectangle. And so in 2D, you see that trivially you could guess the GSO basis, right? You could guess the GSO basis just by looking at a lot of signatures. And what Nguyen and Regev show is that actually it also works in higher dimension, and that given enough signatures, you can actually transform using those signatures. You can compute a function, and if you find the local minimal, the global minima of the local minimas actually of this function, then you're basically recovering the GSO basis. And once you recover the GSO basis, it turns out that the first vector of the GSO basis is actually only the only thing you need here to recover the whole thing. So how does Falcon deal with this attack? Well, as I told you, everything is deterministic. So Falcon introduces some randomness into this sampling. So the Falcon signatures will follow a discrete Gaussian distribution of covariance matrix B transpose sigma B, where B is the secret matrix. And sigma is something that we choose. And it's chosen to avoid the leakage that we have here. So what we start is with the GSO decomposition of B. So in the middle, the matrix D consists of a diagonal matrix consisting of like the eigenvalues of the matrix B. And if we choose sigma to be of this form, then the final distribution will be of B transpose sigma B will be a little sigma squared identity, where little sigma is a parameter that we can choose. And this makes it so that now, as you can see, the Gaussian distribution is independent of the basis. So the signature distribution is going to be independent of the basis. And so we don't have this leakage that we have as we saw in the Nguyen-Regev attack. So Nguyen-Regev doesn't work on Falcon like this. And the problem is now we need to sample a complex Gaussian. So we need to sample, the way we are going to sign in Falcon is that we're going to sample a Gaussian and we're going to multiply it by the matrix B. Hence, we're going to get this B transpose sigma B. So what we need is sample a Gaussian from this distribution. So from this covariance matrix sigma. And the sigma might be a little complicated, right? So the sampler in Falcon is quite complex, but the only thing we need to understand is that it uses what we call a Falcon tree. So it builds at the key generation a Falcon tree. And the leaf values that you can see on the bottom, D1, D2 to Dn, are the diagonal values of the matrix D. And the way we're going to perform this Gaussian sampling is that we're going to start from the leaves. And the leaves are going to be easy to sample. So to sample on the leaves, sampling on the leaves means sampling on the integers with standard deviation of parameter D1, D2, and then we continue. So basically, we're going to perform n samples over Z. Then we did like the first level of the tree. Then we're going to go up. We're going to merge the samples using the intermediate values of the tree. And we don't really care about the steps. I won't really go into the details. But what you need to understand is that we start by performing Gaussian sampling over Z, which is something that is much easier. And the way we sample Gaussians over Z is actually that we're going to sample a fixed width Gaussian, actually a half fixed width Gaussian. So basically, we're going to sample the positive part of a Gaussian. and using a fixed width sigma. And then using rejection sampling, Falcon's allowed to sample from well, a lot of standard deviations. So how to implement this basic Gaussian sampling over Z for fixed width? Well, it's a simple linear scan over a table, which you can define, which you can see as like a simple, very simple Python program. So basically, you sample a uniform value over 72 bits. You have a table that is called RCDT, and you're going to scan in this table. Is your uniform value smaller than the RCDT entry number I? And if so, you're going to add 1 to your sample, and you're going to basically return the sample like this. So this is constant time because you're going through the whole table at each sample. But this is not the hard part of the sampler. This is actually the most easy part of the sampler, because remember that we're sampling a Gaussian of fixed width. So this is very easy. You can compute the distribution, plug in the values in the table, and here is your very basic sampler. And this is going to be the sampler that we have. So one very simple observation that you can see from this code is that if I give you smaller values inside this table RCDT, since we increment each time that the value is larger than your uniform value, then if I give you smaller values, then I'm going to get a smaller Gaussian necessary, right? And this is exactly what we attacked, is that let's say that we're able to modify this table, right? Then we might be able to lower the values, and especially what we ended up using was Rowhammer. So Rowhammer is a type. I'm not an expert. I only know it, like I only read a few papers on it, and the way it works is that basically it allows you, if you see it as a black box thing, it allows you to trigger bit flips inside the RAM. So here we're going to be interested in flipping 1 into zeros, as you can see in the example I illustrated here. And the way it works physically is basically you're accessing neighboring rows of like a target row in the RAM. And these accesses, so if you access them too fast in a weird way, then you're basically going to generate some noise over the row, the target row. And this noise might actually trigger a bit flip. And the funny thing with the Rowhammer attack is that it's surprisingly reproducible. So one thing that we also checked, but I mean, this is a well-known fact, is that you can actually scan the RAM. Like, let's say you have access to some RAM, you can try to perform the Rowhammer attack on every row of the RAM. And sometimes you will notice bit flips from 0 to 1, sometimes from 1 to 0. But one thing that is actually surprising is that once you've identified where the bit flips trigger, they will trigger again if you do the attack. So what you could do if you wanted to attack someone is basically scan the RAM that they're going to use, know where the bit flips are going to get triggered. And this is quite technical. We didn't go into this, but you can actually make it so that the program that you want to attack is allocated in an area that is suitable for this attack. Basically, you can trick the OS into, like you can basically DDoS the OS by asking it too much memory and then freeing the right memory, the one you know is going to be bad, so that the OS allocates it when the victim is going to start the program. So the program is going to get loaded in the right area of the memory, and then you know that since you scan the memory, you know that this Rowhammer attack will go through and will basically do the bit flips that you want. It's very technical. We didn't do the full chain, but we didn't implement the full chain, sorry, but it works. And actually, as you'll see, there has been, like, at the time of the paper, there was one work that actually implemented this attack over FrodoChem, though on the keygen, not on the encryption or the decryption. So we wanted to compare ourselves to this paper, and actually we used it as like an example of what we could expect to be like a reasonable number of bit flips that we could target with Rowhammer, since they actually implemented the full attack. So now the question is, how many bit flips do we need for the attack to work? So the original Nguyen Regev attack, so on the NTRUSign, works if the table is empty, right? So if we have basically no Gaussian, if you take 0 as a Gaussian, then the attack would work because we would come back to the deterministic case, like an NTRUSign type. But of course, this is not realistic, since there are like 72 times 13 bits in the table, we're not going to perform a Rowhammer on all of them. It's like totally impossible. But one scenario that is actually possible is 8-bit flips. This is exactly the scenario of FAR and others at CCS 2022, where they attack the keygen in Fraught, and it's not like random bit flips, it's actually targeted bit flips, which we were surprised that was possible to do. So they really needed like 8 specific bit flips of the key to be flipped in order to start their attack. And they actually were able to do it. So that's what we started with. We started with these 8-bit flips that we allowed to be targeted, as in the scenario of CCS. And this didn't work with the Nguyen Regev attack. So we're not claiming that it would never work. What we observed is that it requires a lot of signatures, and it might require too much signatures for us to compute. The problem of the Nguyen Regev attack that I didn't mention is that you need to store every single signature. So when you're starting to deal with like tens of millions of signatures, the attack becomes impractical, and we could not make it work. And of course, we wanted to consider like the most favorable scenario where you allow yourself 1-bit flip, and well, of course, it didn't work. So the question that we could have is, how does the signature distribution behave with these bit flips? And what happens is not, what I'm going to describe is not exactly true, but I think it's a good intuition of what's actually happening. So remember the Falcon tree, by introducing this error in the table, what we're basically doing is introducing some error in the Falcon tree. It's not true because we're not targeting the Falcon tree, but it's as if we were introducing some error in the Falcon tree. And if we do that, what you can see is that we replace the matrix D in the computation of the sigma covariance matrix by some error matrix E. So it's like D plus some error. And it results in a final covariance matrix that is not little sigma times identity anymore, little sigma squared times identity. It's a different matrix, right? So we call it sigma tilde. And one key observation we had was that now, if you observe this new covariance matrix sigma tilde, then the GSO vectors, the normalized GSO vectors, are the eigenvectors of this matrix. So one simple idea would get that, okay, if I get a good approximation enough of this covariance matrix, then I could extract the GSO by computing its eigenvectors. So it's really easy to get a good approximation of the covariance matrix because you can just use like signatures to do that. And the advantage is that it's quite memory and CPU efficient, because as opposed to the Nguyen Regev attack, we don't need to store everything. We can just refine our approximation of sigma tilde. So we can use billions of signatures, and that's actually something we could do like with our server. So that's an advantage because we can get much better approximation. Like we can handle a lot more signatures, but the problem is that it doesn't work first, which is quite a problem. But the problem is a little bit deeper than what I described here. Is that you know that the eigenvalues are going to converge, and you can get like a kind of an idea of how they're going to converge, how many signatures you need to have like a good approximation. But this is not true about the eigenvectors, and especially because we're handling several eigenspaces of dimension 2, this is even less clear. Like, how are the eigenspaces going to converge, or whatever that means? That we don't know. So let me give you a bit of an illustration of what's happening in the sigma tilde matrix. So for 8-bit flips, the graph you can see, so it's not super clear right now, but this is the distribution of the eigenvalues. So on the x-axis, you have a number from 0 to 1023. And this is the index of the vector in the GSO basis. So the 0 entry corresponds to like the GSO vector number 1, and the last one to the last GSO entry. So as you can see, we see like this slope going down from 0 to 511, and then from 512 to 123, it goes down again. So this is due to the structure of the entry lattice, and we don't really care about that. I just wanted. So this is the situation in 1-bit flip. It's kind of reversed. The slope is going up, and then down, and then up again. And the important thing that you need to remember is that these figures are consistent over all the bases. So once we introduce 8-bit flips, we will always get something like this. Once we introduce 1-bit flip, we always get something like this. And this is important because this allows us to mount the attack. And so back to the shortcomings in Regev. We have really bad results for the full dimension, which is 1024, because Nguyen Regev doesn't work like for a reasonable number of signatures. And the observation that we can have is that we don't need to recover all the vectors of the GSO. We don't actually care about most of the vectors because, for instance, if we could get the first vector of the GSO, we can actually recover the key. But if we get the 10th vector, it's not clear how to do that. So we only care about a small number of vectors that we want to recover. And it would be nice if we could perform the Nguyen Regev search on a smaller subspace because it's much more efficient and it doesn't require like God knows how many signatures, like probably billions of signatures. It requires maybe a few million signatures. Now the problem is how to identify the subspace that we want to work with. So one idea we had is that, okay, we get consistent distribution of eigenvalues and we know which vectors are interesting. For instance, the vector number 511 that you can see is I can't show it with my mouse, but it's like the one at the top, basically the highest value that you can see. This is an interesting value because with it we can recover the full secret key. And so what we could say is, okay, let's fix a threshold. Here it's 100, and say we care only about the eigenvalues that are bigger than 100. Since we know that the graph is, this distribution is consistent. Of course, the threshold might be different, but we can say, okay, we take the 30 biggest eigenvalues. The one we're interested in must be inside this 30 or 32, let's say, eigenvalues. Now, as I told you, the convergence of eigenvalues is much clearer than the convergence of eigenvectors, right? So we know that if we have a good approximation, like a good enough approximation, this value of interest will be inside this set. So once we did this, we have an approximation, right? So we have the real covariance matrix with the real eigenspace, and now we have an approximation with the approximated eigenspace, right? So we fix the parameter k, which like is basically whatever we want, but like let's say 32, 16, whatever feels like good enough so that we get the right the vector of interest, sorry, the eigenvalue of interest into this set. So if the approximated eigenspace v hat was the same as the real one v, then we could project the signatures that we have on v hat and perform the Nguyen Regev attack. So perform this optimization over this smaller subspace. And this, like if we had k equal 32, is very, very, very simple. But in practice, what we have is that v is different than v hat because we don't really know how the approximated eigenspace is going to behave with respect to the original one. Now the question is, how close does it have to be so that we can perform the attack? And there is a result, a very interesting result from Davis Cahan. And so what we care here is that they express the closeness, whatever that means, of these two subspaces that we care about in terms of the error that we have, so the norm of the error of the covariance matrix, so the quality of our approximation, divided by some lambda k minus lambda k plus 1 term, which is basically the last eigenvalue that was took, minus the next one. So the first one we didn't take, assuming that they are ordered by amplitude. And what this Davis-Cahan result says is that these subspace are so close depending on 1 over this gap, this eigenvalue gap. The problem is that in practice, this gap is not so interesting for us because for NTRU lattices, this lambda k minus lambda k plus 1 could be very, very small, which make our subspaces quite far, right? So we're not really happy with this bound because it was very pessimistic and it required, like, it was basically telling us that we need a ton of signatures, and this was really bad. And the reason that it's bad is that in this context, in this theorem, what we're interested in is like the convergence of like the eigenspace, the full eigenspace. But remember that we only care about one vector there. We don't care about the other vectors. So we only need one of the GSO vectors to be in the hat. So at least like we don't need it to be fully in. We need it to be like very close to this eigenspace. And what we got is, I think, quite a cute result, is that the eigenvector that we have, that we are looking for, is close to the approximate eigenspace, the hat. But this time, instead of having like a small eigengap, we get an eigengap that is 1 over lambda 1 minus lambda k plus 1, where lambda 1 is the biggest eigenvalue and lambda k plus 1 is the first one we didn't take. So it's the biggest one we didn't take. And this gap is incredibly large, or smaller here, because that's what we're interested in, right? So this gap is much better for us in our case, and it really gives us a good bound. And this bound allows us to kind of quantify how much signatures we need in order to perform the key recovery. And that we think is really, really nice. So overall, the attack is quite simple. You compute a good approximation of the matrix sigma tilde. So here we call it sigma hat, the approximation sigma hat. From there, you have a parameter k that gives you like the number of eigenvalues you want to consider. You consider the space V hat, that is the eigenspace spanned by those eigenvalues. And what you do is you project the signatures on V hat to perform the Nguyen Regev attack. That's very, very, very simple. And it happens that, well, basically, the attack works in every scenario we have. And we were very surprised that even with one bit flip, we're able to recover the key after some signatures. And I didn't mention exactly when I say 1 bit flip, 8 bit flips, I didn't really give a strategy like, is it random bit flips or not? We decided to adhere to the scenario of CCS 2022 on the attack of Fraught. And basically also use targeted bit flips. So for instance, when I say 1 bit flip, it's going to be, basically the bit flips of the most significant bit of the biggest values, because this is like the best bit flip you could hope for, right? Is going to be the bit flip that is going to reduce the size of the sample the most. Now, how much signatures do we need? So we did the Nguyen Regev attack on the empty table. This required 2 million signatures. And for 8 bit flips, we needed 20 million signatures to have a good estimate of the covariance matrix. So this allowed them to work in a good enough subspace. And in this subspace, we used 2 million signatures. So you can actually reuse some of the signatures. You don't have to sample 22 million signatures. I think I think it worked that you could use the like 2 million signatures from the 20 million set. So you actually need 20 million signatures. And we use a parameter k smaller than 16. Now, for 1 bit flip, you need a significantly larger amount of signatures for the approximation, because the bit flip is making a difference, but still it's quite noisy. And you need 300 million signatures to get a good approximation. And then you can perform the Nguyen Regev attack over 20 million signatures. And for this, you need a larger k. So you need k to be like close to 64, basically. So you need 64 dimensional subspace. Now, also the good thing with this attack is that I think we had pretty nice countermeasures. So we observed that the bit flips reduce signature size. And it's actually very noticeable. It's not like just a tiny bit. It's actually like something like it's dividing the size of the signature by 4 or something like this, even the 1 bit flip that we tried. And another thing that you can observe is that, of course, we're counting on the fact that the bit flips are permanent in RAM. So basically, we're targeting, like the scenario is the target is actually running a lot of signatures on the same program, basically. Let's say it's a server that is always required to output some signatures if you give it some stuff, then it's going to use the same table. Now, the countermeasure to the first one is a lower bound rejection on the size, on the signature size. So if you sample a signature in Falcon, you actually have an upper bound rejection. So if the signature is too big, then the signature will get rejected. But if you also introduce a lower bound rejection, so if the signature is too small, you reject the signature, then you actually break our attack, because we don't have any way of ensuring that the signature is actually of the good size. Every attempt we had, the signatures were really small. So we believe that this is actually a very good countermeasures for this kind of fault ejection attack on the RCDT table, because it would require a lot of granularity on the attack, like really targeting good bits that don't make the signature small enough, but that still allow like a very good leakage, which we think is not really possible. So, and the advantage of this very simple countermeasure, and I think is going to be implemented actually. I don't think it's necessarily only us that made it so, but I think it's going to get implemented, is that it's not affecting the runtime, basically, because signatures should not be that small. And that's actually something interesting, right? Because just having this simple check probably breaks a lot of fault injection attacks on Falcon. And the solution for the second one, so the fact that the bit flips in the RAM are permanent, is that you could also have some kind of integrity check of the RCDT table. I think this might be, depending on how many signatures you want to output per session, it might be costly, it might be very cheap, amortized. Or you could also, enforce that you're not signing too much signatures without like refreshing the table and redrawing it from RAM. This could be a mitigation, but it's a much more, I think it's a less interesting mitigation. So the conclusion is that so we have this nice attack on Falcon. The question is, does it work on other RCDT-based schemes such as Hawk? In the Hawk scenario, it's a bit more complicated because we actually have two RCDTs, and it's not as direct as Falcon because the leakage is much more complicated. And also another thing that we wanted to try is another way to finish the attack. So here we use a Nguyen Regev, but you see that the attack is two steps. Maybe there is a more efficient way to recover the key in the subspace, like something that is not like brute force with the signatures. Maybe, maybe there's a better way to do that, and it would require much less signatures. So thanks for watching the talk, and I think that was also, I guess, if you have any questions, please feel free to ask.
I have a question, Kelvin. Can you go to the eigenvalue attack? Where you presented the eigenvalue thing? Yeah. Just a bit in the back.
Yeah.
Backing, I mean, sorry, that should be forward for your side. Yes. Where you have scan theorem.
Okay, sorry.
Yeah. So I just want to make sure, why do you use this thing and not just just randomly choose some subspace and try things out? I mean, do you need it to be deterministic, or you can just make it randomized? I mean, I'm just curious.
What do you mean? Like,
Just
you
try
mean the
out. Like
choice of...
so the dimension is 1024, right? Like you just take the random subspace and then just try out the attack. If it works, it works, and you just, if it does not, just take a new subspace and just continue.
So basically the problem is that so there's two things. The thing is that you don't really care about most vectors, actually. Like in the 1024, I think like 10 of them are interesting.
I see.
So this is a bit annoying, because if you take a random subspace of like small size, it might, like, there's little chance that you get this vector, but it might work. But the problem is that you need to be sure that this subspace of the approximation is close enough to the original subspace, because if you don't have this, then you have no guarantee that you're going to find the vector. And the way you could see this is, if I give you the subspace with too much noise, then basically I'm not giving you enough information to recover the vector. Like,
okay,
because in the end, you might, like, the vector that you're looking for might not be exactly inside this space, right? It might be up to like some tiny bit, like maybe one coordinate is not here. But one thing I didn't mention is that if you, let's say, recover 123 coordinate of that vector, since we have the NTRU equation, you can recover the rest, right? You don't really care.
Yeah.
So that's that's why we need. I mean, we didn't need the bound to try everything, right? But with the bound, the good thing is that we can actually automate the attack. You can say, okay, if I have this amount of signatures, I'm sure that the vector I'm looking for is going to be like 99.999%
Okay.
inside this space,
So
basically.
it's kind of a very deterministic thing. So you don't need the randomization in some way.
Yeah, exactly.
Okay, makes sense, makes sense. And also, I have a very stupid question. Uh, so here, when you generate the Falcon signature, like it's not
Yeah,
related to that, just related to the Falcon signature. When you generate
yeah,
the Falcon signature,
yeah.
is it have to be deterministic? Is it have to be randomized, or can I just make it deterministic?
You mean the respect to the hash?
The the signature, like it's generated using some kind of Gaussian, right?
Yeah,
So if
yeah.
just giving the Gaussian vector, can I give some kind of seed that's going to generate these Gaussian vectors? I mean, that can reduce the signature size of Falcon, no?
No, the problem is that no, because you cannot output the. I mean, the seed. You could use a seed to compute like. I
Yes,
mean, definitely, like if I give you for instance, the sampler here, like
yes,
the
yes,
basic sampler, you could give like the seed for the uniform, right?
yes.
But the problem is that this is not something you output, right? This is something that is still secret.
No, but if you are using this pseudo-random number generator, suppose like you have that PRG, you're
Yeah,
using this Gaussian distribution, you are using this PRG, so you're just giving out the seed so that anybody can from the seed anybody can just use that to output the
I know,
Gaussian.
no. But the problem is that you would need because the problem is that you need to generate first the signature, and then you need to find a seed that corresponds to this sample.
Okay, I
And
see. Yeah.
and this is hard.
Okay, 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 okay. Makes sense. Makes sense. Is there any other question? Anyone from online? Oh, okay. So if there is no other question, let's thank Kelvin again. And I mean, it was very nice to have you here. We could able to understand like this Rowhammer attack that appeared last year in crypto. Thank you, Kelvin. I hope to see you sometime soon.
Yeah, my pleasure. Thanks.
Thank you so
Thanks,
much.
everyone.
Thank
Thanks.
you.